Hello everyone. In this presentation today, we are gonna talk about well-known pathfinding algorithms and specifically about a search algorithm. So let's start with some definitions. What are these pathfinding algorithms? So usually they are an attempt to solve the shortest path problem in graph theory. They try to find the best path given a starting and ending point based on some predefined criteria. So in a scope of graph theory, the shortest path problem is the problem of finding a path between two vertices, which is pretty obvious, but this path can't be a random one. It should be the one in which the sum of the weights of the graph's edges is minimized. So essentially, all this sentence is trying to say is find the shortest path between two nodes. Talking about the importance of these algorithms, the scope of their usage is pretty big because they are applied in our daily life applications like Google Maps, and their usage grows to the bigger scale of satellite navigation systems and routing packets over the internet. Famous pathfinding algorithms are Dijkstra's algorithm, D-star, and A-star search algorithm. So concentrating on our presentation, we should highlight that A-star search algorithm is one of the best and the most popular technique used in pathfinding and graph traversals. It's often used in computer science due to its completeness, optimality, and optimal efficiency. And going back to the origins of this algorithm, it was created as part of the ZhyZhykina project, which had the aim of building a mobile robot that could plan its own actions. You can see that robot on the picture above. As you can notice, there are two pictures on this slide, and that's where the interesting part starts. So A-star algorithm started with that strange, clumsy, huge robot you can see on the picture above, and it actually ended up in the modern cleaning robots everyone is dreaming about nowadays. So you can see the development and the wide application of this algorithm. So after this presentation, you can say that you know your cleaning robot if you already have one from the inside. So let's dive into the description of this algorithm. So A-star is an informed search algorithm, meaning that it is formulated in terms of weighted graphs, one of which you can observe on the left picture. So the aim of this algorithm is starting from a specific node of a graph. It's A in our example. It aims to find a path to the given goal node. It's K on the picture, having the smallest cost, least distance traveled, shortest time, or something like that. It does this by maintaining a tree of paths, originating at the start node and extending those paths one edge at a time until its termination criterion is satisfied. So what it means is that starting from A node and until you reach the K node, you are traveling from one node to another, choosing the best way that satisfies your criteria. So basically everything is happening in one loop in which your steps of determining the next node are repeated constantly until you reach your goal. So at each iteration of its main loop, A-star needs to determine which of its paths to extend, meaning determining the next node he can travel to. It does so based on the cost of the path and an estimate of the cost required to extend the path all the way to the goal. So basically what you are estimating is the path from the current node to the next node, plus the cost of traveling from the chosen node to the goal one. So specifically, A star selects the path that minimizes f function, which is actually the sum of g and h. So you should remember these three letters and three functions because we are gonna need it till the end of this presentation. The basics, n is the next node on the path, and g from n is the cost of the path from the start node to the node n. Hn is the heuristic function that estimates the cost of the cheapest path from n to the goal. And for a side note, we should mention that Dijkstra is a special case of A-star search algorithm, where h is equal to 0 for all nodes. So basically, in Dijkstra algorithm, all you're estimating is the cost of traveling from the current node to the next one, and you're not taking into attention the cost of traveling from the node you chose to the goal one. As no formula is understood and remembered until it's applied, let us proceed with our example of A-star search algorithm. So as you can see on the picture, we have a weighted graph with 8 nodes and we have 2 edges. It's A starting point and H ending one. To proceed with algorithm, we are repeating the formula from the previous slide, and in every decision we are making during the travel from start point to end point, we are taking into account the meaning of f function. So as we have already mentioned, this f function is the sum of meanings of g and h. And let's apply this on our example. So basically, you can see two types of values on this picture. So yellow ones are the estimates of traveling between two nodes. And each red value represents the cost of traveling from this node to the ending one. So as we mentioned, we are starting in a node A and trying to get to the edge. So the node A have two child nodes, it's B and E. And we are finding the F meaning for these two nodes. So F from B equals to 6 plus 8, which equals 14. So for better understanding, 6 is the cost of traveling from A to B, and the 8 is cost of traveling from B to H. So whenever you see red numbers in our calculations, you should look to the edges of our graph, and every time you see the red ones, you should look to the nodes. Okay, so we are calculating the meaning of f function for these two nodes, and we are making our decision based on the minimal value. So as 9 is less than 14, we are traveling from A to E. Now our starting node is E node, and it has two child nodes, F and G. So we are applying the previous steps to these two child nodes, and we are determining the one with the last F value. The one thing I want to highlight is that the meaning of G function is the sum of all edges you have passed while getting to the current node. So while calculating the cost of the traveling from E node to F, you should not forget about the cost of traveling from A to E. So you should add not only 1 plus 7, but also not forget the number 3. So we have calculating the cost of F functions for F and G nodes, and we are choosing the minimal one, which is F node. So we are traveling from E node to F, and now our starting node is F. So we are repeating the previous steps, and we have 2 child nodes, H and G. And even though one of these child nodes is our goal node, we cannot go straight there because it can be not the shortest path. So we are calculating the cost of traveling from F to H and from F to G, considering the meaning of H function to be 0. And it really turns out that the cheaper way to get to our goal node is not going straight, but going to the G node. As G node has only one child node and it's the ending one, we are just calculating the cost of traveling between these 2 nodes, and here we have our whole path. As mentioned before, this algorithm has a lot of common with Dijkstra algorithm, which I think is better known among you guys. So you might ask, what is so special about this algorithm, and why should I choose it instead of well-known Dijkstra algorithm? So the special feature of A-star search algorithm is that it's a smart algorithm, and it actually separates it from the other conventional algorithm. So A-star can be applied on 2D grid, having several obstacles on the way. So whenever you have the way which has any kind of obstacles on the way, A-star algorithm is what you are looking for. So you are not only calculating the shortest way, but you are also doing it taking the possible obstacles into consideration. So here we have a square grid which possesses many obstacles scattered randomly. And we have the initial and final cell provided. So our aim is to reach the final cell in the shortest amount of time. And as you can see on the picture, we are not setting any limitation for the move. So the decision is made only based on the shortest path, which is calculated by the Euclidean distance formula. You can see that on the move from the point 4,2 to the point 3,3, it's done by diagonal. So here we have an example of calculating the meaning of that heuristic function that estimates the cost of movement from the current node to the goal one. So basically, we can do the calculation of that meaning in 2 ways. So the first one is the calculation of the exact value of heuristic function. And the defect of this approach is that it's really time consuming. And the second one is approximating the value of H using some heuristics. So let me give you some details on these 2 approaches. Talking about exact heuristics, there are two ways of finding the exact value of each function. So the first one is pre-computing the distance between each pair of cells before running the A-star search algorithm. But as you understand, the complexity of this calculation will grow accordingly to the amount of the cells you have. Slightly more efficient way of calculating the exact value is doing it by Euclidean distance. It helps us to avoid some pre-computation, but it can only be done if there are no block cells and obstacles on our way. If you don't want to do a lot of manual work and you want your A-star algorithm to be less time consuming, a good approach is calculating of each value by approximation heuristics. So here we have three types of approximation heuristics, and the use cases they are best matched for. So the first one is Manhattan distance, and it's nothing but the sum of absolute values of differences in the goals x and y coordinates and the current cells x and y coordinates respectively. So here you have the formula of calculating the each value. And this heuristic can be used when we are allowed to move only in 4 directions only. So it's right, left, top, and bottom. You cannot move by diagonal. The second approximation heuristics actually helps with that limitation, and it allows us to move in e directions, similar to a king in chess. So diagonal distance is a maximum of absolute values of differences in the goals x and y coordinates and the current cells x and y coordinates respectively. So we are calculating the x and y's difference and taking the maximum values. The third heuristic you can use for calculating the each value is well known for you, Euclidean distance. The distance between the current cell and the goal cell is done by using the distance formula. And this heuristic can be used only when we are allowed to move in any directions. But as we have mentioned before, this heuristic can only be used when we know for sure that there are no obstacles in our way. So if you are using the A-star algorithm for its special feature, the ability to find the best with the obstacles on the way, you should choose between first two heuristics, Manhattan or diagonal distance heuristics. Now that we are acquainted with the mechanism and all the specifics of A-star search algorithm, it's time for us to talk about the most interesting part, the application of this algorithm. So as it's used to calculate the shortest distance between the source and destination, it's pretty obvious that this algorithm is widely used in maps, but which can seem more interesting for some of you is that this algorithm is used in games. And one example of this is a very popular game, Warcraft 3. And in our game written in C programming language, we actually served to evil with our search algorithm because it helped our ghost to find the Pacman. On this screen, you can see the steps of implementation of A-star algorithm in our console game. And as you can see, it was done with the help of data structure specifically lists, and you can see the flow of the steps, which is pretty the same we have done in our example. So we are starting the game, and as you can see, as soon as the game starts, the ghosts start their hunting. There is not a single second when they are just walking randomly. They are already traveling on the shortest path found by A-star algorithms. So if you stay in your place for a few seconds, you're gonna be dead. So as you can see, this algorithm can be used in the games of such type when someone has to die, when someone is hunting someone, and so on. So that's pretty much everything I wanted to share with you in this presentation. I really hope it was helpful for you, and after it you will start implementation of your own computer game in which someone is definitely doomed to die because he will be found by the fastest path found by our algorithm. Or you can even start programming of your own robot, or even participate on satellite navigation systems. It's up to you. Thank you for your attention.